the lecture concerning the Ising model. And okay, today we are going to, I'm going to start to talk about correlation inequalities. And yeah, a motivation to introduce these inequalities is really the existence of infinite volume Gibbs states. So what are Gibbs states? Well, basically, okay, they are the Ising model, but defined on the whole lattice instead of being defined on the box. So, well, the idea of the book is to make a definition of this that does not rely on measure theory. Okay, so let's go there. So. Infinite volume Gibbs states for the Ising model. Okay, so the first ingredient we are going to need is the notion of local function. Okay, so remember that omega is a state of configuration, of spin configuration on ZD. And we say that f, a real valued function defined on omega, is local. And I will first give an informal definition. If one only needs to know the value of sigma in a finite box to determine f of sigma. Okay, so basically, f is local if I can find a set such that f is completely determined by sigma x, the set of spin values in that box. So let me make this. Does this definition make sense? I will just give a more formal one in a moment, but. Okay, so for 20% of the audience at least, maybe more. Okay, so let me now give a more formal definition. So f is local if there exists lambda finite and a function f from omega lambda to r such that for all sigma in omega, f of sigma is equal to f tilde of sigma x, x in lambda. Okay, this is just exactly what I've said before. So another way to say it, so this would be, which is completely equivalent, is to say that, okay, if you don't want to introduce this function f tilde, okay, just say, Okay, so what this means is that if two spin configurations coincide on lambda, then the F has to be equal for these two spin configurations. Okay, so to go from one definition, okay, this clearly implies that. Okay, and to go, to move away, well, you just define F tilde here to be the common value taken by all configurations that extend the spin configuration that we are considering inside lambda. Okay. This equivalently, if okay. F is local if there exists lambda such that. Okay. And now I call the support of F the minimal possible choice of lambda here. Okay, so smallest okay, so well, the fact that there exists a smaller set is just come from the fact that if this is satisfied for lambda 1 and lambda 2, it's satisfied for the intersection. Okay, so you just take the intersection of all lambdas that satisfy this, and you get the support of F. Okay, and basically, the support of F with this definition, it might be empty. Okay, if you take F a constant function, then the support is empty. Okay? But okay, and maybe one thing. So now this F and this F tilde, they are different things. Okay, F here it's a function defined on omega, and this is a function defined on omega lambda. Okay, but it will be somehow convenient for me sometimes in this class to identify the two. And it will be kind of clear when I will do this. So, I mean, for instance, well, if F is local, and the support of F is included in some box lambda, okay, when I write this, okay, for this to make sense, I would have to consider an element of omega lambda, okay, because this is a measure defined on spin configuration on the finite set lambda, okay? But well, there is a natural correspondence between the two, so okay, this is a small abuse of notation, but I hope you won't be perturbed by it. Okay. So is everybody okay with the definition of local functions? Okay. So now I will define the notion of state. Okay, and for those who know about measure theory, it's just a detour not to define a measure on omega. Yes?
In this definition, the F tilde must be unique.
Yes. So yeah, it can be an exercise to check that this is unique. But you see, yeah, this relation kind of defines F tilde for this, for each configuration. I mean, it's unique, but of course it depends on lambda, okay, in a sense, because its domain of definition depends on lambda. Okay. So what's an infinite volume state? Well, is a functional defined on the set of local functions. Okay, and I want this to satisfy the following. So first thing, okay. So it's a functional which I define by these brackets. Okay, the same bracket that I use for expectation with respect to the Gibbs distribution. Okay, so I want like the bracket of 1 to be equal to 1. Okay, remember these things, it's supposed to be like an expectation. Okay, I'm taking expectation of f of sigma. This is so I want bracket of 1 to be equal to 1. 2, I want the bracket to be linear. So I want that lambda f plus g is equal to lambda f plus g. Okay, for all lambda real and fg local. And the last thing is I want f to be positive if f of sigma is positive, okay, for all sigma in omega. Okay, so not completely, not exactly a measure, but something close enough. And okay, so basically this gives you additivity. You don't have sigma additivity. Okay, and well, this guarantees that you don't have a sign measure. And this is just saying you that the total mass is 1, so you have probability. It's a probability. And yes, I think you can define states that are not measures, but it's not really a matter for us. Okay. So now, given lambda n that converges to ZD. So what I mean here is just that it's increasing and that the union is equal to ZD. So, okay, like not in the Van Hoff sense. I don't require anything on the boundary. So this is okay. Now I'm going to define Gibbs states, and eta n a sequence of boundary condition and a state Okay, we say that mu lambda n beta h eta n converges to the state given by these brackets if for all f local we have that the limit when n goes to infinity of f lambda n beta h eta n is equal to the bracket of f. Okay, and any state which can be expressed as limit of is called a Gibbs state. Okay, so here just a bit of precision. Okay, for this to be well defined, okay, for this to be well defined, I need somehow the support of f to be included in lambda n. Okay? But for the limit to be defined, I don't need all the sequence to be defined. I just need to be defined after for n large enough. So if the sequence lambda n exhausts ZD, then this is defined for n sufficiently large. Okay, so this I can define this limit. Okay? This makes sense only if n is sufficiently large so that the support of f is included in lambda n. Okay, in which case, this is just replaced by the corresponding f tilde, okay, which is different for every n, but it doesn't matter. And okay, I mean, all of this is kind of a bit technical. It's just to say that we are not leaving rigor away, okay, but you're just doing the intuitive thing, the right thing. Okay. So now I'm going to digress a little bit and introduce a special set of local functions that are going to be quite useful. And in fact, there are not only special sets of local functions, there are two. I mean, the set of local function, it's a vector space. Okay? Because just exercise. Okay, it's something that I've implicitly used here. Okay, so for multiplication by a scalar, this is quite obvious. For addition, this is easy still. Okay, so it's a vector space, and the two families of local functions that I'm going to introduce now, they are spatial bases of this vector space. Okay, so I have two of them. So first one is, okay, both of them are indexed by finite subsets of ZD. Okay, and I will write this to say that A is a finite subset of ZD. Okay. So for A finite subset of ZD, we define sigma A, which is just the product over X in A of sigma X, and NA, which is the product over X in A of 1 plus sigma X over 2. Okay, so sigma A is just the product of all the spins in the set A. NA, well, it's the product of these things which are, I will call this N of X, and N of X is just the indicator of plus spins, okay? So N of A, basically, it's equal to 1 if all the spins are plus in A, and it's equal to 0 if not. So, okay, our basis of log of omega. Log of omega is just a set of local functions. More precisely, okay, if f is local, there exists alpha A, F, and alpha A, F, such that F is equal to sum over A of alpha A sigma A, and it's equal also to sum over A alpha A of F and N of A. Okay, so any F, you can write it as a linear combinations of the sigma A's and or of the NA's, okay, and the linear combination is unique, okay, because it's a base, okay, and well, these coefficients, I mean, only finitely many of them are non-zero. Okay, so before proving this, let me use that. Okay, I don't really need it, but it makes the proof cleaner. Let me use this just to show the existence of Gibbs states. Okay, so So, in fact, I'm going to do more than prove the existence of Gibbs states. what I'm going to do to show is that if you give me any sequence of boundary condition and any sequence of lambda n that goes to infinity, I can extract a converging subsequence here. Okay, so I can extract, okay, as long as I consider a subsequence, I will have this kind of convergence for every f. Okay, I need to extract it carefully, okay, but so what I'm going to do now, and the argument is really classic. It's the standard diagonal argument, okay, but I don't know. It's an argument that I like, so. Yeah, if you've not seen it enough time to remember it, I think it's always good to see it once more. So the argument is the following. So I'm just going to write this for this. Okay? Just to simplify. Okay, and I want to show that we want to find a converging subsequence for this. Okay, so the idea, I mean, this is a linear functional on well, the set of local functions whose support is included in lambda n. Okay, so by linearity, in fact, in order to prove the convergence of every f, you only need to prove this for a base of the vector space. Okay, because by linearity, then you will. So by linearity, to prove that yes. Yes. And if you don't have constants, you don't have the base. I hadn't think about it, but it's a very important observation. And I guess n of the empty set is equal to 1. Okay, thank you. Okay, so now what I'm going to do is to I start with an enumeration of the set of finite sets of ZD. So I just take all the finite sets and I order them. Okay, I have finitely many of them, okay, because I have only, I have only, say, 2 to the n square finite sets that are included in the box of, well, 2 to the, okay. I have a finite number of finite sets in a box of radius n, and then I take the union over all n, so I get something which is countable. So I can enumerate this. And now what I have is that sigma a n, I know that this is smaller than 1. Well, the reason, okay, let's make it for NA. This will be easier. So I have that NA is larger than 0 and larger than 1. Okay, so the NA smaller than, okay, NA positive, it's just this. No, this is, okay. Okay, yeah. I'll make it for NA, but this is just an expectation, so this is fine. Okay, NA is smaller than 1, so the expectation with respect to the measure is smaller than 1. Okay, so the important thing is that it's bounded. So what I have is that there exists N1 K such that and no, okay. This way I don't use the letter N for two different things, and I feel better. So using Boltzmann-Weierstrass theorem, I have a sequence that takes value in a compact. So I can just extract a subsequence that converges to a limit. Okay. This is sigma A1. So now I want to make sure that it converges for every A. So if I want to have a sequence that converges for A1 and A2, what I will do is extract a subsequence from this first subsequence. So there exists NK2 subsequence of NK1. So, I mean, NK1, it's an increasing integer valued sequence. And by NK2 subsequence of NK1, I just mean that NK2 is also an increasing sequence, and the set of values it takes is included in the set of values taken by NK1, such that NA2, sigma A2, NK2 converges when k goes to infinity to L2. And in the same manner, I can say that there exists NKI. Okay, I can just at the is step of my process, I will extract a subsequence for, so here I is larger than 3, okay? Sigma A3, sigma AI, and Ki from K to infinity converges to Li. Okay, so now if I look at this sequence Nki, it's a subsequence of Nk1, Nk2 until Nki minus 1. So not only along this sequence, this converges, but in fact, what I have is that this converges for all j in 1j. Okay, and okay, the final step of the argument is really this diagonal ID. So you define just Mk to be equal to Nkk. Okay? So I mean, the idea is that you want to have convergence simultaneously for all I. Basically, you would like to intersect all the subsequences. Problem is that if you do that, you might get some empty thing. Okay? But the idea is that you don't need to be always in each sequence. You just need to be in each sequence after a certain step. Okay? And this diagonal thing just does that for you. Okay? So we have, for all I in larger than 1, sigma AI mk converges to Li. Okay, why? Well, simply because from k larger than I, basically, this thing, all the values, this thing starts to be a subsequence of nki. Okay? I don't know, I cannot say about the first I minus one values, but they don't really matter for this convergence. Okay, and because this goes, basically, you have convergence for every local function just by linearity. Okay, so Gibbs states exist, and this is basically just by a compactness argument. Okay. I mean, what I've just done is basically I've done by hand the proof that. If you take a countable product of compact and you consider it with the product topologies, then it remains compact. Okay, so now let's prove the lemma. And so what we are going to show, so we show that for lambda finite, NA included in lambda and sigma A included in lambda are bases of the set of F local such that support of F is included in lambda. Okay, and this is basically the same thing as the set of functions defined on omega lambda, okay, just by the correspondences I had. So I'm just going to show that this is the base of this space. Okay? And of course, depending on the context, sigma A, you can see it as an element of omega or as an element of omega lambda. Okay, it's not a problem. It's important that A. Okay, so there are abuses of notations everywhere, but they are not really problematic. Okay, so now if you look at this space, okay, the dimension of this vector space is just the cardinality of this. Okay, the set of real valued function on a finite space, the dimension is just the cardinality of this space. So the dimension is just 2 to the lambda. So we actually just need to show that these families generate this space in order to show that they are bases. Okay, just by reasoning on the dimension. Okay, because they have the right cardinality. Okay, and in fact, I only need to prove this thing for sigma A because I know that I know that the n A's can generate the sigma A's. So write this. What I have is that sigma A is equal to the sum over x in A of 2 nx minus 1. Okay, I just replace sigma x by 2nx minus 1, which is the same thing. And just using now binomial expansion, okay, I get that this is a sum over the subsets in A of minus 1 over A minus B to the B and B. Okay? So this is just, well, like the binomial expansion. I mean, it's just the expansion of a polynomial. If you're not used to it, you can look at it later. But okay, it's kind of clear that when you expand this, in fact, you only get things that are of the type NB. Okay, you don't need to know about the coefficients for the argument. Okay, so now let's prove that sigma A forms a base, and the notes are over there. I'm going to rely on some identity, which is the following. So 2 to the minus lambda is equal to the sum over A included in lambda sigma, 2 to the minus lambda times sum over all subsets A of lambda sigma A sigma prime A. It's equal to the indicator of sigma equals sigma prime. Okay. For all sigma prime in omega lambda. Okay, so now for f from omega lambda to r, so let's admit this for a moment. And okay, and if you admit this, then the result is kind of immediate, because if you look at this, okay, if you say that sigma prime is fixed, okay, and okay, if you look at this as a function of sigma, okay, and you make then this as a family of function indexed by sigma prime, it's just the canonical base of your space. Okay, it's just the, if you see it as a vector, it's just the vector that's equal to 1 on sigma prime and 0 on the rest. Okay, so what you're proving here is that with the sigma A's, you can generate the canonical base. Okay, so let's do things with more details, but what you have is that f of sigma, this is just, well, you can decompose it on the canonical base. Okay, and now you can use this expression to write this. So this is equal to sum over sigma prime in omega lambda, 2 to the minus lambda, f of sigma prime, 2 to the minus lambda, sum over A included in lambda, sigma A, sigma prime of A. Okay, and I can just reorganize the sum and say that what I have is just the sum over A included in lambda times 2 to the minus lambda sum over sigma prime in omega lambda, sigma prime of A, sigma A. And maybe here f prime of sigma is needed, f of sigma prime is needed. Okay? So this thing, I think it's my alpha A of f, and I have my decomposition. Okay? What I'm doing is just replacing this by this, and then reorganizing the sum to make the sum over A appears first. Okay, there seems to be lots of doubts about this. Let me check. Okay. The writing is terrible, and there was a cardinality missing, but apart from that. Okay, you can continue to think about this. We are going to prove this star relation. Maybe it can be the source of the puzzle. So,
for example, if A has just, if one is just 1 point,
yes.
and then sum is just 1 term, right?
No, this sum is 2 terms. You have the empty set and the singleton. And you were the one to notice that the empty set was there. Okay, and maybe something I've not been clear about is that I was admitting this for a moment, and now we are going to prove this. Okay, that's simple. Okay, so, well, there are basically 2 cases. So if sigma is equal to sigma prime, then sigma A is equal to sigma prime A, and both of them belongs to -1, 1. Okay? So what you have is that sigma A, sigma prime A is equal to 1. So you have 2 to the lambda terms. They are all equal to 1. Good. Okay, if sigma is not sigma prime, then we can choose x in lambda such that sigma x prime is equal to -1. And now what we have, okay, is that the sum over A in lambda of sigma A, sigma prime A, well, it's equal to the sum over A in lambda such that x is in A, sigma A, sigma prime A, plus the sum over A in lambda minus x, yes, of sigma A, sigma prime A. Okay, maybe I should have, okay, I should have written this term first, but it doesn't matter. Now, the first term, well, a set in lambda which contains x is just a set in lambda that does not contain x and to which I add x. Okay? And in this operation, I mean, there is, okay, so there is a bijection between this collection of sets and this collection of sets. Okay, and the operation is just adding x or taking x away. Okay, so maybe I should put B here. No, this is A and this is B. Okay, so now I said B is equal to A union X. So this is a change of variable. Okay? So what I do is that I have the sum over A in lambda, so, such that okay, in lambda minus x of sigma A union x, sigma prime A union x, plus some, because it's the second term. Sigma A, sigma prime. Okay, just. Okay, and now I can just put everything in factor. So this thing is just sigma A, sigma prime A times sigma x, sigma prime x. Okay, just because this sigma A by definition is multiplicative for disjoint union. So I have the sum over A in lambda minus x over sigma A, sigma prime A times sigma x, sigma prime x. And here I have just the same thing, but just a factor 1. And this is equal to 0, because this is equal to -1. Okay, so I mean, the idea is that there is one coordinate, okay, for which this product is equal to -1. So, I mean, basically, when you're summing over A here, you're kind of summing over, yeah, you have you're summing over kind of, it's like summing over spin configurations. And, okay, so basically, you can factor, okay, basically the idea is that when you sum over this, you can factor every coordinate. Okay, so if one coordinate gives you a contribution 0, then you're done. Okay, and if all coordinates give you contribution 2, then what you get in the end is 1. Okay, so let's take a small break, and then we come back to talk about correlation inequalities. So just 5 minutes. Okay, so let's now talk about correlation inequalities, and let me try to motivate them a little bit. So, okay, so far we are trying to look at Gibbs states, and we know that they exist, but not much more, because the procedure for their existence is some extraction procedure, which you cannot get any information about. So our big questions is whether you have one Gibbs states or several Gibbs states. Okay, whether you get the same limit for every possible set of boundary condition, or if you might get different limit for different set of boundary conditions, or even for one boundary condition, you might get different limit along different subsequences. Okay, so this is a kind of a puzzling question, and this will help us to understand the phase transition. Okay, basically, the phase transition for the Ising model, it's a phase transition in beta, and the idea is that for small beta, we will have uniqueness of Gibbs state, and for large beta, you will have multiplicity of Gibbs states. So now the question is, are there some special Gibbs states which can be identified easily? And the answer is yes. And so for instance, if you consider plus boundary condition, so by plus, okay, plus is just an element of omega, and what you have is that plus of x, okay, is equal to +1 for every x in omega. Okay, if I just want to say that plus is a special choice of eta. Okay, so yes. Okay. So now the idea is that this thing converts to a Gibbs state, which I will call the plus boundary condition Gibbs state. Okay. So why is it so? Well, the idea is that if you take the average of NA here, okay, it is a non-increasing sequence. Okay, so why should it be? Well, the idea is that, you know, in my Hamiltonian, okay, I have the term with h sigma x, which is not so important, but I have this term. And this term kind of tells me that if my neighbors are pluses, I want to be plus as well. So presence of plus in general should help other pluses to come by. Okay? So now the idea is that if I have something in a larger box, okay, I want to say that I will have less. Okay, NA is just the this is just the probability that everybody is plus in A. Okay, So now I can look at this. I can look at this. Okay, what is this guy seeing as a boundary condition on the box lambda n? Okay, and the idea is that this thing is kind of the same thing as the Ising model in lambda n, but with a random boundary condition. Okay, and we'll see that in a moment. But and on this random boundary condition, well, you have less pluses than there, because there you have only pluses. Okay, so for this reason, this has to be larger than this, because this has, if you look at this just restricted on lambda n and its boundary, I mean, this has a boundary which is more plus than this one. Okay, so this will make more pluses appear. So for this to be true, I mean, basically, you need to make a formal claim about this thing that I said, that that pluses help other pluses to appear. Okay? What this is exactly FKG inequality. Okay? So in fact, we are going to see two correlation inequalities. One is FKG, and the other is GKS. And basically, FKG helps you with this kind of monotonicity. GKS gives you monotonicity not for NA, but for sigma A, so it will also be helpful. Okay? So what I'm going to do now is state the theorems and the associated definitions. And then basically show that this theorem implies the fact that this is decreasing, so the fact that this plus boundary plus Gibbs states exist. Okay? Then you will have a plus Gibbs states and a minus Gibbs states, and the idea is that if these two are equal, then you have only one Gibbs state, because all the other possible Gibbs states, they are kind of sandwiched between these two. Okay, so then if you want to prove unicity of Gibbs states, you are left with only proving the fact that the plus Gibbs state is equal to the minus Gibbs state. Okay, so lots of information, but we will spend a lot of time on this, so. This should be fun. Okay, so we have two correlation inequalities. So the first is GKS, which is Griffiths, Kelly, and Sherman. And FKG, which is Fortuyn, Kestelin, and Ginibre. Okay, so this thing is, of course, a generalization of Harris inequality that we have seen for percolation. Okay, so let's start with GKS. So what GKS inequality says is that if H is positive, then for all A included in lambda, what we have is that the average of sigma of A, lambda beta H, with plus boundary condition is positive. And so this is like the first GKS inequality. The second is that for all, okay. Yes, for all A, B, including lambda, sigma A and sigma B are positively correlated, meaning that sigma A lambda beta H plus sigma B lambda beta H plus is larger than sigma A lambda beta H plus sigma B lambda beta H plus. Okay, so as Beatrice rightfully pointed out, I mean, if you define sigma A, sigma for the empty set, if you define sigma for the no, I was going to say something. No, okay. No, so those are two different things. Okay, if B is the empty set, this is trivial. So okay, they are really two inequalities. So okay. So what's important is that this is true only for H larger than 0 and plus boundary condition, or if you prefer, non-negative boundary condition, because this is also valid for 0 boundary condition. Okay. So in fact, I mean, it's valid with a bit more generality. You can see that in the book, and maybe when we will prove it, I will state the result with a full generality. But this is the only case in which we will use it. Okay, so the idea of this inequality is that pluses really help to produce more pluses. Okay, but I mean, here it's not exactly clear what's going on because I mean, these things become positive when you have two minuses. So I don't know. I don't have clear intuition of what exactly this means, but there are some situations in which it's helpful. Okay, and also the proof is relatively simple. Okay, so for me, FKG is kind of the opposite. So the proof, okay, so at least the proof that we are going to see is kind of difficult to understand. But the result is kind of, I don't know, I think it's more intuitive. Well, it should be true. Okay, so of course what we have to recall before introducing FKG inequality is the notion of increasing events and increasing functions. So okay, so first thing, we defined an order on omega lambda, which is just the coordinate orders. It's a partial order. The configuration is larger than another configuration if at all coordinates the spin is larger. Now we say that F is increasing if for all sigma prime in omega lambda, sigma larger than sigma prime implies that f of sigma is larger than f of sigma prime. Okay, and we say that E is increasing if the indicator of E is increasing. So what this means, in other words, is that for all sigma in E, for all sigma in omega lambda, sigma in E implies for all sigma prime in omega lambda, sigma prime larger than sigma implies sigma prime in E. Okay, if a configuration is in E, then all the configurations that are above it are in E. Okay, and associated with this notion, you have, of course, the notion of decreasingness. Okay, you say that a function is decreasing if its opposite is increasing, and you say that an event is decreasing if its complement is increasing. Okay, so f is decreasing if minus f is increasing and E if is increasing. Okay, and this is equivalent to say that the indicator of E is decreasing. You can just check that as an exercise. Okay, so what does FKG inequality says? Well, it says that increasing functions are positively correlated. So, theorem, if f and g are increasing, then what you have is that f g lambda beta h eta is larger than f lambda beta h eta g lambda beta h eta. Okay, and this is for any eta in H. Okay, so this is in a sense more general than GKS because you don't need to worry about the boundary condition or the magnetic field. Okay, here you need positive magnetic fields and a positive boundary condition. Yes, the only thing that needs to be positive is beta, okay, because this is this nearest neighbor interaction that makes plus want to make more plus appears. Okay, if you take beta negatives, then it becomes the opposite. No. This is just because there is no space. This is the product. The product. Oh. Yes. Sorry. Thank you. Sigma A, sigma B, lambda beta h plus is larger than sigma a beta h plus sigma b lambda beta h plus. So this sigma a and sigma b are positively correlated. Okay, if you take the difference between the left and the right-hand side, it's just a covariance between sigma a and sigma b under the Gibbs distribution. The expectation of the product minus the product of the expectations. So just the same thing that we have over there. Okay, except that this is for functions that are not increasing. Okay, so yes, so I forgot to give a few exercises here. So just to exercises. So prove that sigma x. So by sigma x, I mean the function that to sigma associates sigma x. And a are increasing. Prove that sigma a is not increasing if a is larger than 2, the cardinality of a is larger than 2. And 3, prove that the sum of x in a of sigma x, of nx minus na is increasing. Okay, so just a few examples of increasing and not increasing doesn't mean decreasing. Okay, so there are a few corollaries of FKG inequality. So corollaries of FKG. So okay, so like for high-risk inequality, here you can say that well, the expectation of FGH is larger than the expectation of F times the expectation of G times the expectation of H. Or you can do it for any for product of K functions. But for this, you need the functions to be non-negative. Okay, and this is just an easy exercise to prove this by induction. And yes, in your induction, I mean, it's important that your prefactor is positive so that you don't change the size of the. It's important that the expectations here are non-negative so that you don't change the sign of the inequality when you multiply by them. Okay. Also. So this is also valid for two decreasing functions. Okay, I mean, just because you put minuses everywhere and you get increasing functions. Okay, the same is, I mean, if you combine A and B, you get that, okay, basically you can do it for also an arbitrary number of, decreasing functions, provided that they are all non-negative. Okay, I mean, it's not a consequence of A, but the same proof works by induction. Okay, and maybe if F is increasing and G is decreasing, then Fg is smaller than Fg. Okay, if you put, this is also an obvious consequence. If you put a minus in front of one of them, then you just inverse the direction of the inequality. Okay, so yes, now I will talk about what I've just said about, well, the Ising model in one box and in a larger box. This thing that you can see, the one in the smaller box, I mean, that if you look at the larger, the restriction to the smaller box for the Ising model in the larger box, what you get is an Ising model with a random boundary condition. Okay, so I will be more precise about this, and for those who know about Markov chains, this is a kind of Markov property for the Ising model, okay? That if you basically condition about something that appears in part of the box, what you get inside is conditionally independent, and it's an Ising model with a boundary condition given by what you've conditioned on. This should be clear if I write this. If lambda is included in lambda, so, okay. If I have two boxes, lambda prime is a sub-box of lambda, okay, two sets, lambda prime is a subset of lambda. I have one boundary condition, and I have another one, which is such that the two coincide outside of the larger box. So eta x is equal to eta prime of x for all x in omega minus lambda. Okay, what I claim is that mu lambda beta h eta sigma x lambda prime, knowing, okay, let me put y maybe. I mean, it's not really important, but Okay, so let me just do an illustration. So let's assume that I have lambda, which is like this, lambda prime, which is this subbox. Okay, it might even touch lambda somewhere. The boundary might touch. What I'm saying is that if I know that if I look under the large Ising measure, okay, and if I know that what I observe here is eta prime, okay, then what I see inside is just the Ising measure on lambda prime with boundary condition eta prime. Okay, here I have two measures. I'm just saying that these two measures are equal, and this is a measure on. These are two measures on omega lambda prime. Okay. Okay. So what I'm going to do here, okay, I need to prove that these two things are equal, but I already know that this is a probability measure. Okay? Like, so, I will be looking at this thing. So, mu lambda beta h eta sigma x in lambda prime. Sigma y in lambda prime. I want to know the probability that this is equal to sigma prime. Okay, so here, this is a random variable associated to this measure. This is a fixed configuration. Okay, I want to show that this conditional probability is equal to this yes. Okay. I want to show that this is true for all sigma prime in omega lambda prime. Okay? And to show that this is true, in fact, this will be sufficient to show that mu lambda beta h eta of whatever condition to whatever is equal to a constant times exponential h lambda prime beta h eta prime of sigma prime. Okay? If I show this, then I necessarily have this inequality because this constant has to be the right one because I know that this is a probability, that if I sum over sigma prime, I get 1. Okay, so for this reason, I will just not worry about constants. Every time I see something that does not depend on sigma prime, I will just forget about it. Okay. So, for instance, instead of looking at conditional probability, I can look at the intersection. Okay, this is just multiplying by something that does not depend on sigma prime. Okay, so I will just worry about mu of sigma y in lambda prime is equal to sigma prime, and sigma x for all x in lambda minus lambda prime, sigma x is equal to sigma eta prime x. Okay, and now if I look at these intersections, it completely determines the configuration in omega lambda. Okay, so I just have to know to look at the weight of this configuration. Okay, so this thing, it's equal to 1 over z lambda beta h times exponential h lambda beta h eta, and here I have a configuration which are called sigma second, and sigma second is just sigma second is some element of omega lambda, and sigma second of x is equal to, well, sigma prime of x if x is in lambda prime, and it's equal to eta prime of x if x is in lambda minus lambda prime. Okay, just the configuration that are obtained by concatenating this thing and this thing. Okay, so now I can just forget about this, and I want to just extract this Hamiltonian from this one. Okay, so h lambda beta h eta sigma second. Okay, so this is equal to, well, the sum over h. Okay, I will start with the magnetic field because it's the easy part. So the sum over x in lambda times sigma prime of x plus the sum over xy in E lambda sigma x sigma y plus the sum over x y in delta lambda of sigma x eta y. Okay, this is a boundary term. This is a nearest neighbor interaction in the box. This is a magnetic field. Okay, and well, okay. Let's say that this is 2 and this is 3. So basically, what we want to show is that this thing is just equal to this thing plus something that does not depend on sigma prime, and then we're done. Okay, so if you look at 1, this is just equal to h times the sum over x in lambda prime sigma prime of x plus the sum of x in lambda minus lambda prime eta prime of x. Okay, this thing does not depend on sigma prime. This thing is exactly the thing I want. So, well, the magnetic field, the external magnetic field part is kind of done. So we just have to check that for these interaction terms, so for the nearest neighbor interaction term and the boundary term, we get the right thing. Okay, so maybe a first observation is that here eta and eta prime, they are the same thing outside of lambda by definition. So here this is eta prime. Okay, so let's look at 2. Okay, it's kind of clear what we want to prove, so just insist. Okay, so, well, of course, I have the sum over, okay, okay, so I have the sum over xy in E lambda prime of sigma prime x, sigma prime y. Okay, and then I have to care about the rest. Okay, so then I have the sum over, okay, so let's do 2 plus 3 at the same time. Okay, so then I have a sum over edges that are in delta lambda prime. Okay, so these edges, they might be in E lambda or in delta lambda. Okay, depending on whether lambda prime touches, depending on whether the contour of lambda prime touches that of lambda. Okay, so basically, I just take these edges. I mean, I take the sum over those edges which are either there or there. Okay, and then I will have to sum over the rest. So if I do this, I get the sum over xy in delta lambda prime, and then I have sigma prime of x times either this or this, but in both cases, it gives me eta prime. Okay, and then I have sum over x, y in. So I have all the rest. So I have E lambda minus E lambda prime union delta lambda prime of eta prime x, eta prime y. Okay, here I'm summing over edges in E lambda for which both extremities are in lambda minus lambda prime. So this is what I get. And the last thing I get is the rest of term 3 that I've not used there. So the sum over xy in delta lambda minus delta lambda prime of eta x prime, eta y prime. Okay, I'm just summing over all the edges that I've not used so far, and on all these edges, I know that the configuration is fixed to be eta prime. Okay, and I'm done. I mean, this is something that does not depend. Okay, these are things that do not depend on sigma prime, and this plus this is equal to h lambda prime beta h eta prime of sigma prime, which is what we wanted to prove. Okay, so now I'm ready to conclude. If f is increasing and lambda prime is included in lambda, okay, and the support of f is included in lambda prime, then what I want to show, what I have is that if I look at f plus lambda prime, let me not write beta and h so that I can have a board which is a bit cleaner. So what I say is that this is, okay, using the Markov property, what I can say is that this thing, it's the same thing as the average of f for the largest Gibbs measure, but if I condition to have sigma x is equal to plus for all x in lambda prime minus lambda, in lambda minus lambda prime. Okay? Because you know that as far as the restriction to lambda prime is concerned, these two measures are equal. Okay, this is what we have just said. Okay, if you take this larger measure, okay, this is the starting point. If you take this larger measure and you condition to have plus in there, okay, so this plus here is your eta prime, okay? Then it's the same thing as considering this thing, but with boundary condition eta prime, which is plus. Okay. Now, this thing is exactly well, the expectation of f times the indicator of this divided by the expectation of the indicator. Okay? This is definition of conditional probability, but actually the indicator of this event, okay, this is just n lambda minus lambda prime. Okay, so this is just f times n lambda minus lambda prime over n lambda minus lambda prime. Okay, here we have lambda plus lambda plus. Okay, and now this is increasing, so I use FKG inequality, and I get that this is larger than f lambda plus. Okay, so I mean, the Markov property tells you that the Ising measure is in the smaller box. It's the Ising measure in the larger box, but conditioned to an increasing event. And therefore, by FKG inequality, the expectation of increasing functions under these measures under the smaller box, it's smaller than the expected. It's larger than the expectation of increasing function for function in the larger box. Okay? So therefore, if you have an increasing function, then along a sequence of increasing boxes, then the expectation of this function is decreasing. Okay? And because we know that we have a base of increasing functions for the set of local functions, then you have this existence of, you know that, I mean, from this, and I will come back to this, but from this you get the existence of the plus Gibbs state. Okay, I mean, just apply this to lambda n and lambda n plus 1, then you know that this sequence is decreasing in n, and therefore it converges. So you get that all monotone function, the expectation of all monotone function converges, and this is sufficient because the monotone functions span the whole set of, the whole vector space of local functions. Okay, so on Tuesday we are going to prove both correlation inequalities, and then we will move on to basically to prove the existence of phase transition for the Ising model in dimension larger than 2. So, I mean, namely that there is a critical beta for which below this beta you have uniqueness of Gibbs states, and above you have multiplicity of Gibbs states.